Hey everybody, welcome to week 7. That's our guided activity, lab 7. In this lab, we will apply the concept of the sampling distribution and the central limit theorem to test hypotheses using confidence intervals, which you learned all about, and using a z-test, which is a way of using the normal sampling distribution to test hypotheses about data. Let's look at a problem first. Don't forget to load the packages that we're going to need. And let's go from here. So problem 1. Researchers investigating characteristics of gifted children collected data from schools in a large city. They obtained a random sample of 36 children who were identified as gifted soon after they reached the age of 4. One question they're interested in is whether mothers of gifted children also have higher IQs like their kids. That is, if these mothers have IQs that are higher than the typical population. To answer this question, they obtained IQ scores from the mothers of the children in the sample. You will find the simulated IQ data attached, and the parameters used in the simulation were the mean and standard deviation of data reported in the study. So here's the study, and I used the mean and standard deviation to kind of get the data that we are going to use. So let's load the data iqsimulated.csv. The data is right there. Let me actually get rid of everything there in the global environment and load the data so that's all we have there. And then I want you to answer question 1. The sample size for this data set was 38. True or false? If you're looking at the data here, you can see that there is 36 observations. So if you answered false, you are right. It's always useful to double click on the data set just to take a look at it, and you see that it has only one variable, which is the IQ of the various mothers, the 36 mothers of the 36 gifted children that were recruited. So let's get back on track here. Sorry, it's guided activity. So hypothesis testing using confidence intervals. We've just learned all about how to compute confidence intervals when you can get to a sampling distribution applying the central limit theorem, right? So here's what we're going to use confidence intervals to perform a hypothesis test. And this hypothesis test is to evaluate if the data provide convincing evidence that the average IQ of mothers of gifted children is larger than the average IQ score for the population at large, which is 100. So we're going to use a 90% confidence interval to test this hypothesis. So I'm going to set the hypothesis first, actually 2 hypotheses. Take mu. I'm not using the Greek sign, mu, but mu is the average IQ score for the population of all mothers of gifted children. So there is a true mean IQ of all mothers of gifted children, which I do not have access to. But the null hypothesis is that that mean IQ of mothers of gifted children is just the same as the IQ of the general population, which is 100. So that's our null hypothesis. That is, nothing's going on. Their IQ is just the same as the IQ of the general population. The alternative hypothesis, which is directional, is that the average IQ of all mothers in the population is actually greater than the IQ that's typical of the population, greater than 100. So that's step 1 of a hypothesis test. Establish the null and the alternative hypothesis. Step 2, we're going to check conditions and assumptions to estimate the confidence interval based on central limit theorem. Can we use the central limit theorem to construct the sampling distribution of the mean and compute the confidence interval from it. So condition 1 is independence. We cannot measure that directly, but there are some things we can look for in order to ascertain our chances of having independent observations in our data set. And the answer here is that we can assume independence for 2 reasons. The sample is random, and 36 is less than 10% of all mothers of gifted children in the population. Condition 2 has to do with sample size and skew. So I either have to have a pretty normally distributed data set, or that suggests that the particular variable, IQ, is normally distributed in the population, or if our data is skewed, then I need to have a large data set. We're borderline here, we're over 30, so we're considering that we have a largish data set that could deal with slight skews. So let's take a look to see if the data is skewed or not skewed. So to get an idea of the sample distribution, the distribution of data in the sample, and determine its level of skew, we can plot a histogram. So to remind you, the first step to compute a histogram is to compute the range of the data, because then we can decide, at which point the bins start and at which point the bin ends. Remember, we have to have bins to include all of the data. And from that, then we play with bin size until we get a histogram that's not like a broken comb, but has enough details for us to gauge the distribution shape. So to compute the range, I use the function range, and inside the function, it takes as input the actual variable that is inside the data set, data IQ. So data IQ, there is a variable inside that is called IQ, and I want to see the range of the IQ variable. And the range is from 102 all the way to 136. So given this range, we can set bin range from 100, which is below the 102, to all the way up to 140, which is above that. And we typically put these ranges with round numbers. And then we can try different bin sizes, 1, 5, 10, until we find one that looks good. If you don't remember quite right how to do this and play around with these parameters, go back to, I think, our second lab where we did play with this a little bit. Otherwise, just remember that to play with bin size, you just play with this parameter right here. And this is where you put the lower range and the upper range, okay? All right, so here's ggplot. ggplot takes in the data set, the statics that we want to plot. So we want IQ on the x-axis. And then we want histogram, and we want the bins, again, to go from 100 to 140 by 5s. I've tested, so I'm selecting the one I liked. This is the color of the column, the field. This is the title, and then the variable, the labels of the x-axis and y-axis, and I just asked for theme classic. And here we have the histogram. It looks pretty symmetric and normally distributed data. To confirm, we can also look at the mean-median relation. Remember that they are very close to the same if the data is normally distributed. So we will use the function summarize, which you also learned, to tabulate both the mean and the median. So summarize, I'm getting the data set data IQ. I'm asking R to compute the mean of IQ, the median of IQ, and store the mean on the variable mean IQ and the median on the variable median IQ. If I run this, you have your little table, and looking at them, you can see that they are pretty much the same, which reinforces the conclusion that the distribution is normal or minimally not very skewed at all. So remember, we're looking at the conditions, some conditions to determine whether we can use the central limit theorem to build our sampling distribution. And condition number 1 is whether the observations were independent from each other, and we checked that box. And now we want to know if we can assume that either the data is not overly skewed, or if the data sample size is very large, and both of them are true. It's over 30 and not very skewed, nearly normally distributed. So we're checking condition 2 as well. The general conclusion then is that we can use the central limit theorem to estimate the sampling distribution and compute the confidence interval. So just remember that the central limit theorem just tells us that the sampling distribution of the mean is normal, so we have a shape that we can apply the 60, 68, 95, 99.7% rule, so it's normally distributed. The mean of the sampling distribution equals the mean of the population, which we can estimate with the mean of our sample, and the standard deviation of the sampling distribution, which is the standard error, same as the standard error, equals the standard deviation of the population divided by the square root of the sample size. And we can estimate the standard deviation of the population using our sample data because it's large enough for that estimate to be valid. So let's calculate the confidence interval. Here, the 90% confidence interval. So here is the code that every time you need to compute the confidence interval around the mean, when you can assume the conditions for the central limit theorem to be applied, this is the code that you need. We're going to need the mean value of the variable. So we'll take the mean of the variable of interest. We need the z-critical that will embrace the percentage of our data set that relates to the confidence that we want. Here's 90%. So we know that 90% in the middle, there's 10% left over that I will divide from, between the two tails. So I have 0.5 in each tail. And I can use Q norm to get the z-critical. And I'll take the absolute value of that because remember, there will be the negative value on one side, the positive value on the other side. And then I will look at, I can compute the standard deviation of my sample by taking the standard deviation, using the standard deviation function, and using as input the variable in our data set IQ. I know the sample size, it's 36, and I know that the standard error equals the standard deviation that I just computed, divided by the square root of n, which I also defined. With this information in mind, I can compute the lower boundary of the confidence interval, which is mean minus the z-critical, the relevant z-critical, times the standard error. If you're confused about this, you need to go back to the lecture video where I take you through slowly in defining how to compute the formula, going through the formula and everything. Here we're just applying that. The upper confidence interval, it's the mean plus the z-critical we established here times the standard error, which you already computed there. So here I'm trying to set up a vector confidence interval that has the lower bound of the confidence interval and the upper limit of the confidence interval. I'm giving it names, lower and upper, and I'm printing it. So here it is. Lower limit, 116, upper limit, 120 more or less. So with 90% confidence, we can say that the IQ of mothers of gifted children is between 116 and more or less 120. Now, in the independent activity or later on during the exercise we'll do in the guided activity, if I ask you to calculate the confidence interval, this is the code you need to adapt. So pause it, take a minute, and see if you can identify the pieces that you would have to modify. For instance, take a look and determine what is specific to this particular data set, right? So for instance, we'll need the value of the mean because the confidence interval is the mean plus or minus the margin of error. So this stays the same. The function to compute the mean stays the same. But the particular data set that you're going to use and the variable that you need the mean of, that will change. So you have to adapt that. So again, take a minute and figure out what are the pieces that are important to adapt, what pieces might not be important to adapt and can use as is. And we'll practice modifying this later on, but just take a moment and check it out with a little bit more caution and detail. All right? We'll come back on the next video to continue the lab. See you then.